All right. Hello, welcome to Papers We Love 2, the San Francisco chapter of Papers We Love. This is our second meeting since we have rebooted and started meeting again post-pandemic. Today we will be talking about a critique of snapshot isolation. So I hope y'all are very interested in databases and when those databases give you the correct data back, because sometimes it's nice to have databases that actually do the right thing rather than the fast thing. Let's bring on Arjun, who will be presenting to us a critique of snapshot isolation. Take it away.
Thank you, Aaron. Thank you for the wonderful introduction. All right, hey everyone. Today I'll be presenting on the paper A Critique of Snapshot Isolation. It was written by Mason and Daniel from Yahoo Research. And I'm Arjun. I'm working with Metrics Origin. I've been working with Metrics Origin for the last 1.5 years, mostly working on vector and vector indexes and things like that. So this is the agenda. We'll go over some isolation levels and anomalies. Then we'll look into serialization strategies. Then we'll talk about snapshot isolation and serializable snapshot isolation. And we'll come up with an intuitive example to explain how serializable snapshot isolation is implemented. Finally, we'll go over the evaluation numbers. In each of these sections, we'll have a break, and at that time, you can ask questions related to that section. So let's start off with isolation levels. ACID, the term which we all know, when we talk about databases, the first thing that comes to our mind is ACID, and it was coined in 1983. The abbreviation stands for atomicity, consistency, isolation, and durability. Durability is typically guaranteed by writing to a write-ahead log. Atomicity, consistency, and isolation are mostly managed by a transaction manager. Okay, so 1986 was when the first SQL version came out, and like the standard SQL version was like between 1986 and 1989. And it was in 1992 that the foundational SQL standard came out. And this was the SQL version which brought in joins, inner joins, and all those extra operators. And most importantly, this is the paper which brought in transactions. There are further versions like 1999, 2003, and all those things which added few other features like group by window functions and things like that. But yeah, 1992 was the ANSI SQL version which brought in transactions. So one of the problem that they saw in transaction was that serializability was kind of a golden standard. However, serializability was very expensive. According to transaction processing expert Phil Bernstein, he suggested that serializability typically incurs threefold performance penalty when compared to read committed isolation level. So that's when people started exploring weaker isolation levels. And with weaker isolation levels, we associated some sort of an anomaly. And that's what the paper like ANSI SQL 92 talks about. So they added 4 isolation levels and then 3 anomalies. So the isolation levels are read uncommitted, repeatable read, and serializable. Here I have a simple example to talk about each of these anomalies. So let's talk about dirty read. So dirty read comes with read uncommitted. So essentially there is no lock involved. So let's say there are 2 transactions, session A and session B. two transactions running in session A and one in session B. Here you can see that there is an insert happening right here, and then there is a select star happening in the second session. However, the insert is now aborted in the first session. But as you can see, even though this abort happened later in this point, this would not be cascaded onto the session B. So this is like a typical dirty read problem. You might think that why would you need a dirty read? This is really good if you are more like a write heavy workload and you're not bothered about consistency in general. Let's say you're writing some sort of a metrics and the whole focus is on getting the writes faster. Then we have something called as non-repeatable read or fuzzy read. So this comes in the isolation level read committed. So here you can see this is a scenario where we are allocating bonus of 10% for accounts who have the balance more than 1,000. So both the sessions start with begin, and then in this point, session B reads the value. So here you can see that we are getting user IDs whose balance is more than 1,000. However, in the second session, in the first session, there is a write happening for the account number 1234, saying that the balance is going to be 500. Since we already read the user IDs in this point, you will be using the same user IDs in the write, and you can see that apparently the write that happened here did not get reflected here. So that's the problem with non-repeatable or fuzzy read. Then we have something called as fandom reads. So as the name suggests, fandom is like something that comes out of nowhere. So here you have two sessions, session A and session B, and you do a update operation. And then in this session B, you do a read operation. Okay. You are reading all the records which have balance greater than 0. Now you inserted a new record with the balance of 100. However, this would not be, so if you look at both the reads, in both the reads, you have different set of values. Like this read had, let's say, 10 rows, and this read would have 11 rows. This is more like the issue with random reads. Okay, now we'll talk about no anomaly scenario. So no anomaly typically happens when we run the transactions in serializable isolation. So by serializable isolation, I mean the strategy that we used earlier was two-phase locking. So in two-phase locking, you would have locks on reads, writes, and then on top of it, you have something called as range lock. So let's say you have a query which is like select star from something, and there is a where condition. So you apply the locks on all the where clause related scenarios. A typical two-phase lock has a growing phase. This is the point where you get the necessary shared, exclusive, and range locks on the dataset. Then you do the work that you're supposed to do, like do the transaction operation. And then there is a shrinking phase, which is where you do the release of locks. This is the scenario for no anomaly by using serializable transactions. The previous version of SQL, which got released in 1992, that had some anomalies, and that was reported in the paper called A Critique of ANSI SQL Isolation Levels, which was published in 1995. So that paper introduced a few more anomalies like lost update, write skew, etc. And they also introduced two new isolation levels called cursor stability and snapshot isolation. Probably like after 4 years, there was another paper which was published by, it was a PhD thesis from Atul Adya. This is more like a implementation independent specification of existing ANSI SQL isolation levels. And this paper mostly talks about graph-based approach to define isolation level, which is more intuitive, and this kind of brought a new standard to all the ANSI SQL standards, ANSI SQL isolation levels. But that's just a side note. So we are coming back to the 1995 paper, Critique of ANSI SQL Isolation. Okay. So yeah, one of the anomaly that was introduced was lost update. So here I have an example where there is 2 transactions. The first transaction reads X, and it updates its value as, so initial value of X is 100. It updates its value as 115. Then transaction B reads X. It also reads X as 100, and it updates the value as 75, and it writes the value 75. However, when this transaction writes the value, it does not honor the previous value, which is 75. It indeed writes the value 115. This is the problem caused by lost update. And cursor stability is an isolation level which prevents lost update. Okay, so coming to the main isolation level, which is described in our original paper, Critique of Snapshot Isolation. This is snapshot isolation in the, it's like the one that's defined in ANSI SQL paper. So the basic idea is that before reading from the database, you get something called as start timestamp. And before writing to the database, you get something called as commit timestamp. Okay. So every transaction has the start timestamp, and it will read from a particular snapshot based on that start timestamp. And when you write records to the database, you do a write conflict check. So in this case, it's called first committer wins. Basically, whoever writes the data first into the particular row will win. The second write that happens after the transaction will fail. So the basic idea was that it would prevent the lost updates by doing this write conflict detection. So simply said, it can be thought of something like a race. So all of them has this something called a start timestamp and commit timestamp. The guy who wrote commit timestamp first will eventually win the race. However, that had an issue. The snapshot isolation had something called as write skew anomaly. So in this example, I have 2 doctors, Alice and Bob. So the transaction could, each of the transaction runs with the logic that if both the doctors are on call, then you can make one of them off call. Like you can unset on call for one of the doctor. So here you can see that in T1 and T2, we read the same R, which is basically we check whether doctors, count of the doctors who are on call. So in this case, both of them will return 2. Now we have a condition which checks if X is greater than or equal to 2, then we have to set on call equal to false for Alice. In the second transaction, we have on call equal to false for Bob. Here you can see that basically we are updating writes in different rows, but we read from the same read set. And this is called write skew anomaly. fixing the snapshot isolation. So fixing the anomaly in snapshot isolation could be done by doing a read-write conflict check, which is essentially we check if the data which was read in the previous steps, was it modified or not. If that was modified, then yeah, it means that you have to abort. So that was the fix for fixing this write skew anomaly in snapshot isolation, and that would bring serializability guarantee. However, the paper says that a naive implementation of read-write conflict would result probably would result in read operations also having some sort of a lock. So this was not a good strategy, and it need to be well designed so that we can make the best use of read-write conflict and get the performance serializability guarantees. So why is that having locks on read-only transactions is a problem? So if you look at the benchmarks, like PPCE benchmark has around 77% of transactions as read-only. And in the case of Google Megastore, which serves like 23 billion transactions, about 86% of them are read-only transactions. So read-only transaction needs to be log-free, or it should be really performant. And that was one core thing that this paper highlights. Okay, so the critique of snapshot isolation essentially analyzes both write-write conflict detection and read-write conflict detections, and finally it comes to a conclusion that if we are able to replace write-write conflict detection to read-write conflict, you will probably get a serializable isolation level, and they call it as so in the paper, they call the previous snapshot isolation as read snapshot isolation, and the new snapshot isolation, which has this read-write conflict detection, as write snapshot isolation. So yeah, so we just talked about dirty read, lost update, fuzzy read, phantom read, write skew, and no anomaly scenario. And yeah, as I was mentioning, they call the previous snapshot isolation as read snapshot isolation, and they introduced this new read-write conflict detection snapshot isolation as write snapshot isolation, and that is serializable. All right, so any questions so far in the previous section? Okay.
They were
Then
able
I'll
to do the read transactions without taking any locks?
Yeah, we are able to. Okay. So yeah, now we'll look into some serialization strategy. This is kind of a generalization of a couple of papers which talk about serialization and things like that. The idea is more relatable, but it might not depict the actual corner cases and all those details, nitty-gritty details that paper talks about. So don't take it too seriously. But yeah, I'll start off with the quote that isolations are tricky. That's why we have like two critique papers just on isolation, one criticizing CSQL isolation and the other criticizing the snapshot isolation. One of the easiest and the simplest way to get serializability is by sequential execution. At Store, which is like a predecessor of WolTB, implemented a design which partitioned the data and assigned a single core with the single threaded execution engine for each partition. And that execution engine would be responsible for sequentially executing a transaction which is particularly targeted towards a single partition. So yeah, it's a main memory database. For them, acquiring logs found to be pretty time consuming, And one of the strategy that they used was making use of multi-core architecture and main memory systems, and probably partitioning the data, having each partition have a single threaded execution engine and things like that. However, when it comes to multi-partition transactions, they need to do something like a two-phase commit. So two-phase commit is a protocol generally executed by distributed transactions. We have a coordinator and we have a couple of participants. So in the first phase, you send a prepare request to all the participants, and you get the response saying whether it was able to log few records in the participant machine or not. If it was, then if everyone says that it is able to prepare, then it enters the next phase, which is sending out commit or about request. But this two-phase commit had a problem. The problem was that in case of a coordinator failure, you will need to wait until a new coordinator kicks in and recovers from the uh, log and all those things. And also, if one of the participant uh, goes down, then it kind of halts the performance of the whole transactions. Percolator was one system which implemented two-phase commit. And in the case of Percolator, they maintained log tables in the participant nodes. So uh, each of the row had a column called log and write. So essentially, there is a key column, there is a data column, then there is a log column, and then there is a write column. So write column would store the last write timestamp. Log column is kind of the log like column which will be used for two-phase logging and things like that. And yeah, participants used to store log information in the actual table itself. Now, in order to prevent the coordinator failure scenario and things like that, there was this thing called pre-phase commit. So it adds a new pre-commit phase, and it also adds timeout so that we recover more faster from the coordinator failure. However, this had higher message overhead because there were like 3 phases involved. So that's when people started making all the individual components of two-phase commit highly available. So all the participants and coordinator were like running in a Paxos group or a Raft group, and this ensure that they are highly available and failure of one node will not impact the transaction performance. Okay, so but all these were like log-based approaches, and generally the log-based approach had problems about deadlock, starvation, and if one of the log, if we fail to acquire a log, or if a transaction slows down, it prevents the progress of other transactions. And yeah, if you look at so that's when we need to kind of come up with a different strategy, which is like optimistic concurrency control. Okay, but before going there, let's try to understand what is serializable. So serializable is a guarantee which states that if transactions were to execute in parallel, and if we were to still line them up in a timeline, we could have some sort of dedicated point in timeline to show that this transaction happened at that point. So it can be thought of as like a Git commit. So when you start a Git project, you get some sort of a read timestamp. You clone the project at that particular read timestamp. You work on all the changes in your local workspace, And then when you want to do a commit, you create a pull request, and yeah, people approve your pull request. And the moment you get all approval, that can be thought of as commit timestamp, and that will be merged into the master. And in the middle, if there is a conflict, this conflict resolution happens. And if you look at so there will be multiple participants who will be doing this operations. And finally, if you look at the commit history, you can see that even though all the people worked on different branches and all those things, you'll have a sequential number of commit history to see the timeline of changes. And that's exactly how a serializable transaction also would look like. Now we'll look into some different approaches instead of log-based. So here is a comparison of log-based strategy versus timestamp-based strategy. Okay, so a typical log-based strategy is more like an eager or a pessimistic strategy. Okay, so there is a growing phase where you kind of acquire logs from all the guys who need to agree uh, on your work. Then once you get all the logs, you do the work and then you shrink it. This is done when you have higher chances of conflict. It's more like a pessimistic scenario. But if you have lower chances of conflict, you can go with the timestamp based approach. So the basic idea is that before starting the work, you get some sort of a timestamp. Okay. In basic timestamp ordering algorithm, the concept is that you validate the serialization order as in when you access the record. So whenever you do the work, you will probably read the record or write record or something of that sort. So whenever you do those kind of access operation, you do the validation. And that's the basic idea of timestamp ordering. And finally, once you have validated and completed the work, you do the commit. Okay. Now, optimistic concurrency control is a more lazy approach. So it also gets timestamp in the beginning of the work, and you do the work without doing any validation checks and things like that. You do the validation only after you complete the work. And once you see that there is no conflict, you do the commit. Okay. So validation might use logs or might not use log, but the whole idea is that you have reduced the critical section to a smaller portion. Okay. Now another strategy of gaining serializability is by scheduling. It's called concurrency by scheduling. So it's also more like an eager approach. So basically you split the timestamp into smaller batches called epochs. So in let's say you split the timestamp into a 10 millisecond batch or something of that sort. You order the transaction within the batch so that there is no conflict, and then you do the work. So this strategy is kind of used in Calvin, I guess. So yeah, this basic timestamp ordering, I'm just having a small example. So basically, the idea is that every object is tagged with the read timestamp and write timestamp, and whenever you access the record, you'll update the read timestamp and write timestamp accordingly. And during the access, you will do the validation check, and yeah, that's the basic idea of basic timestamp ordering. Optimistic concurrency control has like conflict detection towards the end, and conflict detection could be done by building something called as precedence graph. So precedence graph can be thought of as like a dependency graph where each node is like a transaction, and within the transactions there will be edges connecting different transactions based on whether there is a read-write dependency or write-write dependency, etc. within the transaction. So this paper, like the Adia's paper that I mentioned, that proposed representing this in the form of serialization history graph, and you can use this precedence graph to do the conflict check and all. So basically the idea is that if you have a loop, then you will probably have to abort one of the transaction, because that will not result in a serializable order. Yeah, but precedence graph was expensive in the practical implementation, and that's when Cahill in 2008 came up with a different strategy. So he introduced this concept called dangerous structure. So the idea was that instead of building the whole graph, it would just check for transactions with income, like it would just build some sort of a dangerous structure graph which has this read write anti-dependency edge. So if a transaction has both incoming and outgoing read write anti-dependency edge, then one of the transaction needs to abort. So the paper talks the idea of having two Boolean flags. One is in conflict and the other is out conflict for each of the transaction. Okay. So this paper is an entire paper on its own, but the basic idea is that if there is a read write anti-dependency between T1 and T3, you will set out conflict as 1 for T1, and then you will set in conflict as 1 for T3. And by any chance, if there is a read write anti-dependency between T3 and T2, you will do the same thing, setting out conflict as 1 and in conflict as 1. So at this point, if T3 were to have both in conflict and out conflict as 1, then T3 should abort. So that was the basic idea of dangerous structure, and it was more easier to build dynamically based on transactions which were available in the memory. So yeah, this is just the graph which talks about serialization by using dangerous structure. Now comes different conflict detection strategy, which is sending read writes to a central oracle and then doing a conflict detection there. So yeah, the central oracle could have some set of recently committed transactions, and it could do the conflict detection based on the recently committed transaction, and it could end up in either commit or an abort. And yeah, we'll be discussing more details about this approach in the upcoming slides. So if you see this image that I have on the right, it's more like a clock with the stack of stones. Clock is more depiction of the timestamp allocation done by the oracle, and the stack of stones is more like a recently committed transactions. And finally, the one which I was talking, concurrency by scheduling. So Calvin is one such paper which does that. So basically it splits timestamp into smaller time units, and it orders the transactions within that time unit batches. And this is done by the sequencing layer. And yeah, that's one strategy. However, the problem is that you need to know both read write set before performing the transaction, and that might not be the case for general application development. So yeah, Calvin is suited for certain use cases only. Okay, so just to summarize the techniques that we have seen so far. So there is one which basically, if you can execute transactions sequentially within a shard or a partition, that's the best strategy. Then we have a lock-based approach, which essentially gains lock and then does the work and releases lock. Then there is timestamp-based strategy. There are, like we talked about, basic timestamp ordering. optimistic concurrency control using graph testing, optimistic concurrency control using central manager. And then finally, we discussed about batching and scheduling, the one strategy which is used by Calvin.
What is the dimension that arrow represents?
Okay, it really doesn't.
Because it seems to vaguely be low latency techniques to high throughput techniques, but
okay, I never intended to have any meaning for that. I just wanted to list down all the strategies. Yeah. Okay. But yeah, you can think of it like something of that sort. But yeah, this strategy is basically having this condition that you need to know the read write set before knowing before doing the transaction, which is like not the case with the other guys, right? So yeah. Okay. So any questions, or can I proceed with the next? Yeah. All right. So the regular snapshot isolation, basically it needs two timestamps. One is the start timestamp and the other is commit timestamp. And it also does this overlap condition check. Basically, there is a spatial overlap check, and then there is a temporal overlap check. Okay. Yeah, this is the simplest way of describing what the overlaps look like. So let's say if two transactions are going to write on the same row, then there is a spatial overlap. And if the transaction commit timestamps kind of overlap with one another, then there is something called as temporal overlap. Okay, so that's the basic overlap condition that was described here. And as I was talking from the beginning, start timestamp is required before reading snapshot from the transaction. So yeah, start timestamp is required before reading, uh, and then commit timestamp is the timestamp which is acquired just before the commit and after the conflict check. Okay. So Percolator implements log-based snapshot isolation. So the apart from regular columns, which is key and value, Percolator has log and write, which is two additional column families added to each row. So log will be used for two-phase commit, and write is essentially used to store the latest commit timestamp. And this will be used for write conflict check. So the basic idea is that you get the timestamp, you do the read operation based on the snapshot, uh, based on that read timestamp. And when you do a write, you will be updating this write with the commit timestamp. And when the second transaction tries to write, it detects a conflict based on the write timestamp, and it will abort. So this was about log-based snapshot isolation. However, there is a different strategy to do snapshot isolation, which was using a central oracle. So Yahoo Research implemented or like published a paper which talks about log-free snapshot isolation. Note that it's not log-free serializable snapshot isolation. It's log-free snapshot isolation, which is like a predecessor of the current paper that we are discussing. Okay, so the basic idea was that you would during the commit, you would send write set to a central oracle where it will be checked against where it will be performed with the conflict detection algorithm, and finally it will be assigned the commit timestamp at an atomic manner. So this is the algorithm. Basically, you can see that R stands for writes or the write set, So basically what we are doing is for each of the records in the write set, you are going to check whether the last commit timestamp is more than the read timestamp of the transaction. If that is the case, then that means that a transaction has modified the read set of the current transaction, and it will need to abort. And finally, here you can see that finally when you do the conflict detection, you will start with the process of getting commit timestamp. So once you get the commit timestamp, you will apply the commit timestamp to all the records which are in the write set. One thing to note that is here both in the hand conflict detection and in the atomic write, there is write set being used. Okay. So essentially, this is the part which is doing some sort of a conflict detection. As you can see, this commit happened before this commit. So the timestamp would be updated in the right last commit of R. And once the second transaction tries to commit, it sees that the start timestamp has the start timestamp and this previous commit timestamp results in a conflict, and that needs to abort. Okay, so now we'll talk about log-free serializable snapshot isolation. So that's the core strategy that's discussed in the paper that we are discussing. Okay, so it involves 3 conditions for overlap check. Basically, these are the 3 conditions. This is called spatial overlap, this is called temporal, and then we should always have write. It shouldn't be a read-only transaction. So yeah, simply say the conditions are that if one transaction writes to a row and another transaction reads from that row, then that's kind of a spatial overlap. And this condition checks whether the commit timestamps overlap. So yeah, here you can see that this guy committed, and then the second transaction is trying to commit after that. And the third condition is more like this condition which says that it shouldn't be a read-only transaction. If it's a read-only transaction, you need not go through all the conflict detection and things like that. So these are the 3 conditions for log-free serializable snapshot isolation. So the basic idea is that transaction doesn't commit if the read set is modified. So yeah, that's the basic idea of doing read-write conflict detection and serializable snapshot isolation. So this is the algorithm. Okay, so on the left-hand side, I have the regular snapshot isolation, which we discussed earlier. And on the right-hand side, we have the new snapshot isolation, which is serializable and which does the read-write conflict detection. So previously, so both the algorithms kind of look similar. There are subtle changes, however. So if you look in this older algorithm, we were just checking the write sets, which is in both conflict check and in the writing, we were just focusing on write set alone. Okay, but in the new algorithm, we'll be doing conflict check on read set, and then we'll be doing the writes on write set. Okay, so you can see the subscript here, which is RR, and in this case it is RW. So the basic idea is that you loop through all the read set and then check if the last commit timestamp of read set is more than the start timestamp. If that's the case, then you need to abort. Else yeah, try on else proceed with the application of proceed with the writing procedure, proceed with the atomic write. So now you get the commit timestamp. You loop through all the write set in the transaction, and then finally update the write time last commit timestamp all the write set elements. Okay. Finally, this paper also talks about different traffics. So there is read-only traffic. So in this case, both read set and write set would be empty, and this will not be impacted by the write snapshot isolation. So this is expected to perform really well. Then there is a typical OLTP workload. In this case, the read set would be somewhere around 20 rows. Write set also would be somewhere around 20 rows, meaning like both read set and write set are relatively smaller. And this strategy is mainly focused towards running OLTP workload kind of thing. Okay. And then it also talks about analytical workload. However, the problem with analytical workload is that there could be queries which would be scanning the whole table, and then that would require you to have a really large read set. So you might be sending a read set which is the whole table rows, and sending those big read set would be very network. Uh, it would impact the network really bad. So one of the strategy that they talk about is probably sending some sort of an over approximated representation of the read set. And in that way, you can reduce the network payload and uh, improve the performance. And the second thing they discuss is that you can probably separate out OLTP and OLAP workload in two different oracles, and so that like OLTP OLAP workload doesn't impact the current OLTP transaction, as OLAP workload might require a more aggressive conflict detection, as it is having a large read set and things like that. Okay. So any questions on this thing? All right, I'll proceed. Okay, so now we'll talk about some implementation details. So yeah, so the basic idea of the last algorithm was that you would check the last commit timestamp of the write set of the read set, right? But this last commit timestamp would be most likely written into the database. So just going back, so here you can see that this last commit timestamp would be probably fetched from the database, and that fetching process could be expensive, especially if your database or the underlying storage layer is something like an HBase or something of that sort. So the paper talks about a strategy where you maintain the last n committed rows and or n committed transactions, and you do the conflict detection on that alone. So the new algorithm essentially checks if there is if the last commit of the particular row is null or not. If it's not null, that means that it is there in the memory. So if it's there in the memory, you do the conflict detection. And if it's not there in the memory, you have something called as Tmax, which is the representation of the last maximum timestamp, which was sent to the storage. So yeah, you can, if you can come, if you don't have the last committed transaction, last committed read timestamp in the Oracle in memory, then you can use this comparison and you can quickly abort the transaction.
How do you know when it's safe to remove a transaction from the history?
Good question. So so the paper kind of skips on a lot of implementation details, and I have dedicated slides towards the subsequent slides, I explain that in more detail. So yeah. The second thing is bookkeeper. So yeah, the Oracle could become a central bottleneck, and it could, if it fails, then the whole transaction gets interrupted. So one strategy was to save it in a distributed write-ahead log, something like a bookkeeper, and yeah, that was one proposal. So coming to the more practical implementation of this algorithm. So we have here an Oracle. Oracle is like a data structure, or like, yeah, Oracle is the central Oracle. And this would be the fields in the Oracle. It will have some sort of a counter which is responsible for giving the next timestamp. It will have something called as read timestamp marker, and this is like a min heap, and it's used to capture the last minimum read times minimum read timestamp. Okay. And then we have something called as commit visibility marker. It is like a waiter. It is used to synchronize visibility of transaction. And then finally we have a stack of recently committed transaction. Okay. This implementation is kind of taken from Badger and a few of the projects that I mentioned here. Transaction structure would look like this. So basically it has a read write flag. So basically if it's just a flag to determine if it's a read-only transaction or a read-write transaction. Then we have begin timestamp, which is like the timestamp which it uses to fetch the snapshot. And let's ignore this part for now. And then there is workspace. So workspace will have the write set, read set, and the snapshot. Okay. Okay, so let's start with the process of acquiring a read timestamp. So first step you do is you get the next timestamp. So here you can see that you get the begin timestamp, which is the next timestamp. Then you add the begin timestamp to the min heap. So there is a read timestamp marker, right? This is more like a min heap. You just add it to that min heap. This min heap will be used to used at later stage to garbage collect older committed transaction. Okay, I'll go to the I'll explain that when that slide comes. And then you do the commit wait. So essentially this is waiting for all the ready to commit transaction to commit. So basically transactions which have the commit timestamp set and it's not yet applied, but yeah, it just waits until all the changes are applied onto the database. So this guarantees that once you get the read timestamp, you are able to see all the transactions which happened before that timestamp. Now let's talk about typical read operation. So the first thing that you do is you get the read timestamp. Then you call snapshot with the corresponding read timestamp, and from the MB store, which is multi-version store. Now you get the snapshot of the multi-version store. Now you create a transaction which has the details, like basically it just has read write as false, it has the read timestamp and other details, and then you return that. So it's like a view is like having a function which has the corresponding transaction as input. Transaction, what is it called? Anonymous function as input. Okay, so this would be how a get would look like. This would be how a get would look like in a transaction. So there is key, and a key is the argument to the get. And the first thing that you do is check whether it's a read-write transaction. So if it's a read-write transaction, first thing you do is you check if the key is present in the write set. If it is present in the write set, then you return the value because that's the write that you made within your transaction workspace. And then you add the corresponding key into the read set of the transaction, because this read set and write set would be sent on to the central oracle for the conflict detection part. If the value is not present, then it's better to return the value from the snapshot, which we got by using the read timestamp. This is how a write timestamp would look like. Essentially,
Is the
sorry, write
assumption here
operation.
that the oracle might be on a different machine across a network?
Yeah. So in this case, this code is for a storage engine. So in the case of Badger, all the Oracle and all those things are within the same machine. Okay.
Thank you.
This is the write operation. So yeah, in the case of write operation, also we get the read timestamp, we get the snapshot, we create a transaction, and we pass the transaction as a function. So within the transaction, we have this set function which has key and value. We first check if it's a read-write transaction or not. If it's a read-write, if it's not a read-write transaction, and if you're setting, just throw a read-only transaction error kind of another. And yeah, when you are calling the set, you are essentially writing data into the write set, and then yeah, that's pretty much it for the write operation. Now we'll talk about the commit operation. Okay, the first thing that you'll do is check if the write set is empty or not. If it's not, if it's empty, then you just throw an empty transaction error or something of that sort. Then you retrieve something called as commit timestamp. In the commit timestamp retrieval process, you will do the conflict detection and things like that. And once you get the commit timestamp, you will send this to a serial single-threaded executor. So this single-threaded executor would be responsible for executing the transactions one after the other based on the commit timestamp. And finally, what you do is you close the commit timestamp. Basically, it just updates. So yeah, when you close the commit timestamp, this is more like saying that the commit is finally applied, and this portion would be used in this part. So yeah, the commit visibility waiter would make use of the previous done part. Okay. Okay, now we'll look into how a commit timestamp is retrieved. So the first step is to lock the particular oracle. Okay, then we do a conflict detection. So when we do a conflict detection, we essentially do the read-write conflict detection part. Then we say that we close the read timestamp of the original transaction. Essentially, this means that we are done with the read for the particular transaction, and that would mean that like the min heap value would essentially get updated. And then we do something called as garbage collect the old transaction. So essentially what we do is we clean up the transactions based on the read timestamp from the min heap. So yeah, basically we pick all the transactions which are no longer relevant, and we remove them from our oracle. Finally, in this part, we'll generate the commit timestamp, and then we'll add the commit timestamp to the visibility marker. So this is the part where you add commit timestamp to the visibility marker. And finally, yeah, this is the part where you say that, okay, I am completed with the change. So I can close the commit timestamp marker. This is the part where we do the conflict check. Basically, this is the original algorithm code, and this is the code from Badger. So basically what we do is we loop through all the transactions which are there in the Oracle. We check if the transactions timestamp, commit timestamp is lesser than the current transactions timestamp, the current transactions begin timestamp. That means if it's not having an overlap, we just skip it. Okay. And if there is an overlap, basically we check if the current transactions read set is part of any of the committed transactions write set. If that's the case, then there is a read-write conflict, and then we do an abort. Okay, this is the part where we do the garbage collection. So essentially what we do is the one min heap that I was talking earlier, right? So we fetch the minimum timestamp which was last read, and then we loop through all the committed transactions and we find transactions whose commit timestamp is lesser than the minimum timestamp which we are having right now in the Oracle, and then we remove the older committed transactions. Okay, I know the code might be a little confusing and all, so that's why I thought of having a simpler example which is more relatable, I guess. So this is an example of cashier, like a banking scenario where there is a cashier. He acts like a central oracle, and then there are a couple of transactions which are happening outside of the bank. So there is transaction where A sends $10 to B, A sends $20 to C, etc. There is a pile of transactions which are sent to the oracle, and there is something called as commit waiter, and all those entities are part of this example. Okay. Okay, so let's start with the mock skit here. We have the cashier, and let's say A wants to send money to B. Let's say A wants to send $10 to B. What's the first step that he does? He will need to find what is the balance in his account. So that's where he sends for a read timestamp. So essentially there is a counter. He gets some sort of a token. Then he let's say the token is right now 7. Okay, but before 7 there are some transactions which are not yet committed, but it has been like finalized in some sort. So they have this commit timestamp. So if 7 was to be returned right away, then it might miss the changes from all these transactions. So what we do is we do a commit wait. So that's the place where like commit wait kicks in. So essentially all the transactions which had this commit timestamp is now applied, and now this read timestamp is now received at the cashier end or something of that sort. And finally, you get back a snapshot of the account balance. So this guarantees that you have seen all the transactions which is before the read timestamp. Okay, that's about the snapshot. When you have the snapshot, you start doing some work. Okay, let's say if you want to transact if you want to send money okay, let's say if you want to send $10 from A to B, then there is a from and to. It can be thought of as read and write set, something of that sort. And yeah, meanwhile, when you are doing the work in your own workspace, there could be other transactions which might come in the way as well. Okay, so those transactions are kind of piled up in the cashier's desk. So we have so 8 and 9 were the commit timestamps. Now 8 and 9 is kind of piled up in the cashier's desk. Now let's say you want to do the commit. Okay, So the first thing that you do is you send the request to the Oracle. Now, when the cashier receives the request, he just need to check for transactions which are there in his desk, like previous transactions were 8 and 9. So essentially, he does the conflict detection in this list of checks which are there in his desk only. Now, once he does the conflict detection, he can assign a commit timestamp to the particular transaction. Okay. At this point, you can say that the transaction is almost committed, but it might not be applied to the original bank or something of that sort. Now, this is the point where read run or garbage collection kicks in. So basically, at this point, you can say that I'm done with the read of my transaction. So I can just close my read timestamp for the min heap or something of that sort. And when you close the read timestamp, you can trigger the garbage collection. So garbage collection basically picks up the checks which are having the timestamp before 7 or something. So if in that case, you will see some transactions, some of the older transactions being removed from the cashier's desk. And yeah, finally, once the commit timestamp is received and all those things, it will be sent on to the single threaded executor, which applies the transaction. And this is the point where you say that you close the commit timestamp as well. So when you close
So
the
we're
commit
keeping track
timestamp,
of some kind of high watermark that says all of the
exactly.
transactions below this number have either committed or aborted. But
Right,
above
right.
this number, there may be transactions that have neither committed nor aborted.
Right. So yeah, the
And the high
watermark,
watermark just keeps rising.
yeah, it can be thought of as a sliding window kind of strategy. So yeah, within a period, you will have a certain set of transactions which you need to do a conflict detection with, because yeah, that's having like between the lowest read timestamp and like the commit timestamp kind of thing. All right, so yeah, executor applies the transaction. And finally, once it applies, it just returns back the commit success back to the user. Okay, so yeah, that's pretty much a intuitive example for like how the algorithm works. And any questions on this? All right, I think that's a no, and I'll proceed with the evaluation. All right, so the expected evaluation results were that read-only transactions are never going to be aborted by either read snapshot isolation or write snapshot isolation. And write snapshot isolation and read snapshot isolation could have some same level of concurrency. That was kind of the expected output from the benchmarks. Okay, so these were the workloads used. One was a read-only workload where all the operations are read-only. And then we had a complex workload which consisted of 50% read and 50% write operation. And each operation would have like n rows, and n is like a uniform number between 0 to 20. So yeah, that would be like, that's how the workload or the benchmark workload look like. So the evaluation aimed to answer these two questions. What's the overload of checking read-write conflict in write snapshot isolation compared to the write-write conflict in snapshot isolation? And what is the level of concurrency offered by WSI when compared to snapshot isolation? So yeah, so the average read timestamp from Central Oracle was having a latency of 0.17 millisecond, and commit timestamp was having a latency of 4.1 millisecond. So why commit timestamp had a relatively higher latency was that before sending back the response, it had to write the record into the bookkeeper. So that was adding more like a network overhead and things like that. In the case of read timestamp, it also need to be written to the bookkeeper, but read timestamps could be generated in batches, and for the batch you can just write once into the bookkeeper. So that's why we have this small difference in read timestamp and commit timestamp.
You wouldn't have
Also
to know off the top of your head if this was done on a spinning disk or an SSD, because that 4.1 milliseconds is suspiciously close to the rotational time of a disk.
I see. I believe the okay, I have not added the screenshot of the machine spec in this slide, but yeah, I just know that on the top of my head, I just know that it was run with HBase as the underlying storage, but I am not sure whether it was using SSD or HDD. But yeah.
Thank you.
All right. So yeah. So the first set of experiment was basically focused on understanding the overhead of status oracle. So here you can see a graph which has throughput in TPS and latency in milliseconds. And the number of clients for the benchmark increased from 1 to 64 exponentially. And the basic idea is that when the number of clients increases, throughput also increases. And but yeah, however, if you note the graph, after around 80K TPS, you can see that the throughput is not increasing well. And you can see that latency is increasing as well. So one of the, so yeah, the blue line is WSI and the red line is our regular snapshot isolation. One of the reasons that they say that the throughput of WSA was a little lower than snapshot isolation was that in the case of WSI, you had to send both read and write set to the central oracle, and it was kind of yeah. So basically, you were required to load twice the memory items for doing the conflict detection check, and that was one of the reason for this small gap in the WSI versus snapshot isolation throughput percentage. One suggestion that they had for increasing the scalability of the system was to partition the database and use a status oracle, individual status oracle for each of the partition. And by any chance, probably if you have a multi-partition transaction, you will probably end up having to use two-phase commit or something of that sort. But yeah, this was just one suggestion which was added in the paper to improve the performance. Now we'll the previous experiment was run with just status oracle alone. It was not the complete setup which involved all the storage node and all those things. This experiment involved using the complete setup, which is having the HBase and all those things. So yeah, basically the number of clients increased in this case from 5 to 650, 640. And you can see that the graphs are pretty much aligned, as in like write-snapshot isolation and snapshot isolation are kind of having similar performance. However, one thing that noted is that after 320 clients, the performance of HP's servers started to saturate, and yeah, that was kind of the limit for the performance numbers. As for the abort rate, we have this like, okay, so in the previous scenario, there is normal distribution, Zipf distribution, and Zipf latest distribution. So a normal distribution is like, I guess probably just randomly doing the query and things like that. Zipf has this pattern where like you have a more frequent transaction and then more frequent row and less frequent rows, something of that sort. And Zipf latest is probably a transaction set where the right set, sorry, yeah, Zipf latest, intuitively, the idea of Zipf latest is that it will result in a conflict for sure. So it will result in a serializability conflict. And that was the main idea of Zipf latest distribution. So comparing the abort rate, essentially both the Zipf and Zipf latest are kind of similar, but abort rate in Zipf latest seems to increase more quickly. One of the reasons was that in the case of Zipf latest, the read set is selected mostly from the recent write set, which means that you will more likely have the write snapshot isolation conflict. So that's why you have this abort rate a little more for WSI. All right, so finally, to summarize this paper, serializability was expensive in the case of two-phase locking, and that's why people tried coming up with weaker isolation levels and anomalies. Among them, there was snapshot isolation, and snapshot isolation, however, had this anomaly called as right skew anomaly. This paper mainly analyzes read-write conflict versus write-write conflict, and claims that with read-write conflict you can achieve serializability, and also it doesn't impact read-only transaction, which is comprising of majority of the workload for large distributed databases. WSI and RSI are performing almost comparable, and finally, serializability could be brought to a lock-free transaction system without hurting the performance. All right, so that concludes my talk. Any questions, comments, feedback?
So it's lock free, but you definitely could still starve someone out because they would just keep getting their transactions aborted.
So
like if you have enough contention on something, sometimes it's nice to be able to just run a lock and then each take turns rather than constantly having this lottery of who makes forward progress.
Right. So the idea of lock free in this algorithm is basically this thing. So in the case of two-phase locking, there is a lock table or lock column particularly designated for each row in the participant table, table, right? But that's not the case for this lock-free algorithm. In the case of lock-free algorithm, we do all the conflict detection and all those things in the central oracle. So yeah, that's the main idea.
I guess my fear is that there's going to be some really complicated transaction, like a database migration, that just keeps getting aborted forever because there's lots of tiny transactions that are doing minor things. And the thing that is the very big transaction that touches everything just gets starved.
Yeah, that could be a possible scenario, but this paper mainly talks about having like a OLTP only workload. Like it's best suited for read-only workloads and OLTP only workloads. Like if the transaction is going to be a long-running transaction, then yeah, it
The
says
answer is
that
sort of, well, don't do those.
yeah, like particularly, yeah, in this slide, right? So they very specifically say that if you have some sort of a long running transaction or OLTP or OLAP transaction, then it's better to separate the workload into a separate Oracle and do that way. Yeah.
Yeah, thank you.
Thank you. Transaction is a very wide space. Like there are a lot of papers out there. Yeah, it was nice. All right, thank you guys.
Thanks
All
a
right.
lot.
Let's thank our speaker again, and then I will stop the recording.
Thank you.
Yeah, that was quite a lot. Long
Yeah.
paper.